Hello everyone, and welcome to this week's Science Hour. This is the CosmoQuest Science Hour that is brought to you each week by either myself or Emily Lakdawalla of the Planetary Society. I'm Dr. Pamela Gay, and I'm on the faculty at Southern Illinois University, Edwardsville. This week, we're going to spend the next hour talking about how the New Horizons mission is going to see not just Pluto, but hopefully some additional Kuiper Belt objects out in the icy parts of our outer solar system. Helping us have this discussion are mission scientists. From my left, working towards the center, we have Dr. Alex Parker, who is the New Horizons Outer Solar System Science Fellow at the Harvard-Smithsonian Center for Astrophysics, back in my hometown of, well, greater metropolitan Boston, which includes Cambridge and Somerville. Also with us this week is JJ Kavelars, an astronomer at the National Research Council of Canada, making sure that, as always, we have a Canadian on the show. So I'd like to thank both of you for being here and start by just having you give us some general background on the New Horizons mission.
Okay, I guess I could start off by just talking about the mission itself a little bit. The main goal of New Horizons is to try to understand more about the surface properties and composition of Pluto, really. Trying to understand Pluto's surfaces, its atmosphere, what's causing changes on Pluto, how things on Pluto are evolving. So that's really, the primary goal. When the New Horizons mission was first conceived, the mission specialist or the mission announcer who talked about the launch actually said the words, New Horizons on its way to the last unexplored planet in the solar system. And that really was what New Horizons started off as. It's a mission to try to, finish the solar inventory, to go to the last planet, see how it's doing, and find out how that particular planet operates. But it's a completely different kind of world. Alex, maybe you want to talk about how different Pluto is.
Well, I just love the fact that during the launch sequence, and we include this in our promotional video for ice investigators, which we'll get to later in the show, it was still a planet when New Horizons launched, and so during the past several years that that New Horizons has been flying through the solar system, Pluto's gotten itself into a little bit of trouble and declassified by some and maintained as a planet by others. So that must have been an incredible roller coaster. Now Alex, you're young to the project. Can you tell me what it's been like coming on board and being part of the team that's working to explore the outer solar system?
Sure. Well, I was an undergraduate when Pluto was reclassified as a dwarf planet, and I did my grad studies in that post environment, and I remember that the first Division of Planetary Sciences meeting I went to, when someone gave a talk, you had to pick a little LED placard that scrolled across with a message, and there was one camp that you could have which says Pluto is a planet, and the other one said Pluto is not a planet, and so you had to stake your camp before you gave your talk. I didn't give a talk that time, so I didn't have to didn't have to immediately jump into the fray, but ever since we've more and more, this had been the sense in the community for a long time, but the impression has been spreading to the general public that Pluto is one of a member of a family of planets, or dwarf planets and minor planets out beyond Neptune, and so this mission remains one to a body of very significant importance, as it was the first member of this population ever discovered, and it remains sort of one of the most key, it's one of the biggest members, and remains a valuable sort of point on that distribution of what we want to understand in the Kuiper Belt. And since then, since the mission launched, we've discovered that Pluto not only has its satellite Charon, which was discovered decades ago, but it has a whole entourage of satellites, and all of these are much smaller and much more, we think, much more like the other small icy bodies that inhabit the outer solar system. And so we're getting kind of a menagerie of objects for the price of one. As we fly by Pluto, we get this whole slew of things to study, and then hopefully we will have other encounters either before and after the Pluto encounter with other objects, small objects, that inhabit the edge of the solar system.
Now, one of the things that's really awesome about the New Horizons mission is this is really the last unexplored corner of our solar system. 50 years ago this summer, Mariner 2 took off, became the first spacecraft to journey to another world within our solar system. And since then, we've explored asteroids, we've explored comets, we've seen all of the planets except for Pluto and the Kuiper belt. That's the last place that humanity hasn't made it.
You know, eventually we'll get out to the Oort cloud, so don't stop at Kuiper belt. Let's just keep on going. And that's what's the reason that the New Horizons ice investigators sort of activities taking place. Right, we're trying to find another object to go to after Pluto, and the truth is that this spacecraft is going extraordinarily fast. Like, it's not just that, oh, this is a pretty quick trip to Pluto. No, this is the fastest man-made object launched from the Earth at the time that it was launched. This is as fast as you can go crossing the solar system. And eventually, this will be the most distant man-made object from the Earth. And we will just continue to explore the solar system with it. So the search, I mean, it's funny, we had, the launch took place quite a while ago, and it was, we'll find a candidate for this thing to encounter. And normally with these kinds of missions, you're talking about a couple decades to work on this problem. No, the timescale just keeps ramping up, and the urgency to do this search, to get the candidate found, goes up and up and up. So.
And I have to say, this may be the scariest mission profile I've ever heard. It even makes like MSL's crazy landing stuff look easy. This mission, how many decades has it been in the works? Do you know when the idea first started getting kicked around to propose for it?
I know there was some stuff talked about in the 70s, looking at trying to get this mission off the ground at that time.
So it's been in the works for a long time.
Yes.
And when the mission took off, it said as part of the profile, we are going to Pluto, and then we're going to budget extensions, senior review, politics willing, and all of our hopes are on that. You're going to go to one, possibly two additional objects that you have sufficient fuel to reach that haven't been discovered.
Yes.
What were you all thinking when you did that?
Well, one of the remarkable things as well, and having come into the community in the mid 2000s, is even since I started undergrad and started studying the solar system, our understanding of the structure of the Kuiper belt has been in flux.
Yes, that's
true.
So
the number of objects that we think are out there has changed. The orbital distribution that we think they have has changed. And so if I were to extrapolate that back or look at the literature from when New Horizons launched, I think we think the Kuiper belt is a very different place today. Maybe not fundamentally different, but certainly in the details different. And so
what are the biggest details that have changed?
Well, the number of quite small objects, and by small I mean sort of a few kilometers across, that number has dropped drastically since the early 2000s. And it wasn't so much that we expected there to be an enormous number of these things, but certainly if we took the trends that we saw from the larger objects and just carried them on down to smaller sizes, we would expect far more than we see. Yeah. And so there's a change in behavior of how many objects there are as a function of size once you get around a certain size. And so there aren't as many small objects. But the mission isn't planning to visit a few kilometer object. Yeah. We're looking more in the order of 100-kilometer object. And so the number of those objects hasn't changed wildly since then. But we've broken down the Kuiper belt into more detailed sort of subregions, and we have ideas that there are multiple populations. It's not just a homogeneous single monolith of chunks of ice out there. Yeah. There are different subgroups that have different orbital properties and different surface properties. And so one of the things that might be nice to do if we had two that we could visit, or if we had some that we could choose from, it would be nice to pick one from multiple populations.
Now, we have Dean Callahan, who's one of our listeners, asking, so is this really a zoom-by, not a fly-by? And how much delta V does the mission have left to navigate the Kuiper Belt interplanetary transport system?
Go ahead, Alex.
The fuel left on board they budget out to pass the Pluto encounter because they will have to consume some fuel as they fly through the Pluto system, and so they don't actually know spot on how much is going to be used. They can only estimate how much will be used. There will be last-minute course corrections and such. But the estimate right now is of order 100 to 120 meters per second, delta V. And for a spacecraft that's traveling 13 kilometers per second, more or less straight out of the solar system, that's not a big tweak on your trajectory. It's a very tiny, about a half a degree variation in the angle at which it's traveling. So it's a very narrow cone of the Kuiper belt that we can visit. And yes, a zoom by would certainly be the best way to describe it. So it'll, like I said, we're traveling outward at 13 kilometers per second, and that speed isn't changing very rapidly. So the encounter will happen very quickly.
Yeah. Now, one of the things that's kind of awesome about this is there's a whole team of you who have been making observations at some of the world's largest and highest resolutions observatories all over the planet, and you clearly aren't observing the entire sky. That would be tedious. Explain how the region of the sky that you are observing was selected, and exactly what it is that's going into trying to find these ice cubes in the ocean.
So the trick is basically to figure out what sort of objects are encounterable by the spacecraft. So you know how much change in velocity you can make. And so what you want to do is say, okay, how big a kind of a cone on the sky is that going to make when we're flying, when the spacecraft's flying along through the solar system? And let's plot that cone, and it's going to kind of change its angle with respect to the Earth slightly as it goes out into space. So we're changing that little cone. And let's look at all the objects that are in some part of the solar system now, but when the spacecraft is going along, they could be in that cone when the spacecraft is going through that part of the cone. And so you're kind of doing this little, you're like, okay, we're here, and these guys are coming along here, and we hope, oh yes, this one will intersect, so those are the ones we want to look for. Now the cone's really small, and so there's not really a large region of space where there are orbits that things could be going through today where they would actually end up going through the cone in the future. And the closer you get to the time of encounter, the smaller the kind of precursor area is than it is now. So if you look for this, if you tried to do this search, say 5 years ago, you had to look over a very large chunk of the sky, like a couple of about 10 degrees squared in the sky. Now it's shrunk down.
For comparison, is about half a degree.
Yeah, you moved to half a degree. So you're looking at an area which is many times the size of the moon. And for these kind of high precision telescopes, that's an enormous area to cover.
Yeah.
But now, as the trajectory, as the time of encounter gets closer and closer, the area of the sky that you need to search starts to shrink and shrink. And so now it's down to just last summer it was a degree and a little bit in size, and now it's shrunk down a little bit further still. And so right now, basically, is the best time to look with current cameras that we have, because they're basically the search area is starting to match the size of cameras that we have for looking at a part of the sky. Now, I was just going to say though, it's actually still pretty horrible though, because it turns out that part of the sky is the galactic center.
Yeah, this is what I was going to say. This is the busiest part of the sky, and the galactic center, for those of you who don't know, is in the constellation Sagittarius. And if you have a brand new pair of binoculars, this is the best place to look, because there's like nebulas and star clusters and gorgeous, shiny, faint fuzzies everywhere, and Kuiper belt objects.
We hope.
We hope. Well, we know. We found a good few so far in these fields, and I'm actually just going to dig up an image here. Which this is not precisely of the fields that we're searching. We had some time last month at Magellan, and before our fields rose, there was another object that's in a very similar part of the sky, but was up just a little bit earlier. So we went to see if we could recover it, just to improve on its orbit. And this is not an object we can encounter from New Horizons, so we were just doing this for science in time that we couldn't use to do the New Horizons project. So when you are acquiring a field on the sky, sometimes you want to look up a finder chart or something and check to make sure that the area of sky is fine. But with this kind of science, we don't really care. We just want to point the telescope where we think the thing should be, take a few pictures, see if we see it. And so we pointed the telescope, and we started downloading the images from the camera, and it was just a mess, and it was an absolute horrid mess. And I mean, it was not only was there thousands and thousands of stars, but there was all this fuzzy junk. And so I was like, where are we looking? And so I brought up WikiSky, and I put in the coordinates, and the object, the Kuiper belt object, had fallen smack in the middle of the Lagoon Nebula.
Oh, no.
So we were pointed, this is the image that came off the telescope. This is a Facebook link, but it should work just fine. I've posted it in the chat there.
Okay.
So we were trying to take color observations, so we were taking images through multiple filters. So in the end, I can make this kind of pretty montage. And unfortunately, I have not been able to, I've since tried to reduce this data and locate the object in it, but the field is so full of nebulosity and stars that I have not been able to locate the object in it.
Oh, no.
But this is the kind of thing that we're dealing with.
Yeah, I mean, there's a paradox that you're taught about when you're doing undergraduate astronomy called Obler's paradox, which is that if you think about the sky, if you look in any direction, there should be a star along that line of sight. And so that means every line of sight, every little line, because there's so many stars in the universe, should eventually intersect the star. So why don't we see stars all over the whole sky? Absorbing that light. So all that light that's being absorbed by the star, by the dust, is kind of resolving that paradox. But when you look towards the galactic center, it's like there is no paradox. It is full of stars.
The dust argument used to hold any more. That was the original proposal, was that it must be that the universe is opaque and that you can't see very far. But once we realized that the universe was not full of dust, the paradox kind of came to the fore again. But what has resolved, the modern resolution for it is simply that the universe has a finite age. So that if the universe is infinite extent and you look in any direction, you will eventually run into the photosphere of a star. But because the universe is finite in age, the light from that star has not yet reached your detector. So if the universe was infinite in age and infinite in extent, you would expect the entire sky to be as bright as the surface of the sun. So fortunately, we don't live in an infinitely old universe.
So this is just one of those images that you look at, and on one hand, it's like, wow, it's stunning. On the other hand, it's like, oh, dear Lord.
Yeah.
And
we have to find the tiny little moving dot in that, and that was quite difficult and so far impossible. But
Now, one thing that you sent ahead of time that I'm also going to try and share, and I apologize for the random going to the wrong screen. We had a report of a wrong URL on Twitter, and I just sent out the correct link. So any of you, so sorry if you ended up coming in late due to a bad URL. And we would ask, as we always do during this brief station identification, this is the CosmoQuest Weekly Science Hangout, Science Hour rather, and if you could share that this hangout is going on with your lists, we'd love to help increase the number of people who are taking this moment out of their week to learn a little bit about this universe that we all share. Now, one of the parts of sharing it is we share it with icy objects. They are moving. The ones this team of people are trying to find for New Horizons are moving through an amazingly busy part of the sky. And I have a video of one of them moving that if you can prep this, if you can explain this image while I share it, I'd greatly appreciate it, Alex.
So this one was an object that I turned up during my reduction of some of the data. And it was a nice bright detection, and so I thought I would share it with the group. So essentially, what I'm showing is what amounts to a time-lapse image. And so this was taken with the Magellan 6.5-meter BADA telescope and the IMAX camera. And this object is somewhere around 40 AU from the sun on a low inclination orbit. So in this image, it looks like it's going up and down, but in fact, the image is rotated 90 degrees from the ecliptic. So its motion is almost directly east to west. And so this is essentially what we see when we're looking for these sorts of moving objects. This is a very nice bright example. Some of the ones that we have are much fainter and much more difficult to see. But what you can see there in the middle is the moving object blinking through the image and the relatively stationary stars sitting around it. And there's some wiggling going on due to the atmosphere varying between these images. But otherwise, what we have are essentially static images taken over time, and we can remove the stationary stars by subtracting the stationary image off. And what we're left with are just objects that move or change in brightness. And then we can link together those detections of objects which moved and determine what kind of orbits they're on and if they're on the kind of orbits that we're interested in.
Now, can you give our listeners and viewers a sense of how wide in arc seconds is, or in arc minutes, this particular image is?
Unfortunately, I don't have that information for this particular thing, but I could guess just by the pixel scale that it's probably of order 10 arc seconds on a side or so, the box there. The total motion is probably about 3 or 4 arc seconds.
So to explain arc second, an arc second is the width of one strand of hair held at arm's length. So they are looking for something very, very small in a very vast sky. And this is an amazing challenge. And one of the problems with this challenge is you end up with these giant images trying to cover that full 1 degree. So 1 degree is 60 arc minutes, which each arc minute is 60 arc seconds. So that's 3,600 arc seconds across. That little sucker you just viewed was 3 arc seconds. You're trying to look for something very small in a very large image. Now, is this something that you can program computers to do?
Yes. So that detection was made by my automated pipeline, and so there are 3 sorts of teams that are analyzing different chunks of data. So JJ is running one effort from Victoria. I'm myself and my supervisor here at the CFA are running another effort, and then at Southwest Research Institute, Mark Bowie is running a third. And we all have our different pipelines that approach this in different ways. And so I'm not familiar with the current state of JJ's pipeline, but I know that of Mark and I's, mine is the more automated. So I can essentially remove the stationary sources and detect moving sources in a fairly highly automated way, and that means that it's only me that has to come back and go and vet all of these things by eye and confirm them. And the data volume is not so, once I've filtered out all the things that I think are stationary and I've run this automated detection pipeline, the number of things that I have to view by eye and confirm is relatively small. Other approaches take a different, they take a different tack where, so for example, Mark Bowie's, he views every single pixel that was collected by the camera by eye and looks through
and he's working with David Bornkamp, so he does have, I believe, a postdoc or a graduate student?
He's a minion of some sort.
He has a minion with whom he has a minion he tortures.
Yes. So it's a massive headache to view all of these images again and again, especially since the one that I showed you there was colored orange because I kind of like that color scheme, but really it's just they're black and white levels. Yeah. And you're essentially just looking at screens of gray blobs and white noise and trying to tease out something that looks more real than something else. And so there's an enormous amount of eye strain and fatigue that goes into this if you have to dig through it on your lonesome.
Now, not everyone's doing it on their lonesome, and not everyone's using computer algorithms. Mm-hmm. What are the benefits of doing it by eye versus doing it by computer? So,
since I'm one of the people feeding all those images into the very loyal ICE investigators out there, well, what computer algorithms do is they detect the thing that you told it to look for. That's what they're good for. And if you know exactly what you're looking for, what the shape is going to be, and how it's going to be appear on the image, then yeah, you could probably design an algorithm that's going to do that reasonably well. But if you're not sure what your source is really going to look like, or you know that kind of source looks a lot like noise, like extraordinarily similar to noise, then computer algorithms start to fail. But the human brain, if it's trained, can actually start to develop its own kind of internal algorithms that are difficult to write, and basically do better. So, and in fact, what we're doing with ICE investigators in our group is we're actually we have a little competition going The ICE investigators are plowing through the data. They've gone through about, I think they've gone through almost half the observations that were sent in, And whereas I have two postdocs at the data center who are churning away through through a much larger chunk of the data, but essentially it'll boil down to the same thing. And so they've been working on this now for a couple of months. And what they're doing is they're running a computerized detection algorithm that measures all kinds of parameters about everything that it detects. And then they're giving it to a machine learning system, which they're trying to train to recognize what objects look like.
Okay.
And so they're using this machine learning system. And what they found is using the machine learning tools, they can train a machine that it will detect 90% of the things that are in the image, which is actually pretty damn fantastic. Unfortunately, it also classifies 10% of the noise as images, as real things as well. Yeah. And our noise signal is something on the order of 1,000 times higher than our actual signal. Oh, and dear. So for every 100 things that you'd have to look at and humanly kind of evaluate, one of them turns out to be legitimate. So that's just not good enough in terms of, that's just too many things to look at. So what we're doing with the ICE investigators is we've given them the same images, or a very similar set of images, and said, you guys, you know what, turn your brains on these things and click on the things that you think look like real sources. And then we'll tell a computer, okay, computer, this is what real things look like, okay? All that other stuff that you've been calling signal, that's not it. And we'll try to train the computer to be more like a human, because we've noticed that humans can get it down to something like 4 or 5 noise things for every one real thing. And at that point, there are other strategies that we can develop where we basically reobserve that object and say, is it still, if it was a real object, it should go from one spot to the next. If it do that, if it did, then yeah, that's a real thing. The noise things, they never really do that, so that's how we eliminate them. But when it's 100 times your signal, that strategy kind of falls apart too. So.
And I'm screen sharing an image here that has a KPO just right there waiting for me to mark it. And that was just sheer, I just opened the software up. It's cosmoquest.org/ICE investigators. And this, I'll move the marking around so the motion will help you see it. This thing right here with nice sharp edges, that's the type of thing that we're looking for. And so by going to this site, you're going to see what may be one of the ugliest scientific images you will ever see that isn't a spectrum. and well, you know it's true. And the thing is that these amazingly ugly images are host to potential targets for a spacecraft to go visit. And that's just really kind of awesome, is you can spend your spare time, laptop in your lap, on the sofa, watching TV while looking at the images, going back and forth, because no one can not multitask nowadays, and use those spare brain cycles you have to help explore our universe.
Yeah. Now, actually, if you can leave that up for, you just went to, there's another one. Okay, that's okay. Yeah. So now on this one, you can see there's actually 3 or 4 things that I would click on. And basically, I don't want to kind of pollute the public into thinking the same way I do, but
I'm an astronomer, so I click on stuff.
Good. And there's actually a third one there that's right by that big bright blob near the top on my screen. It's the top left of the image. It might be the top right on yours. Below the blob, just a little bit lower, and then over to the right a bit.
That?
There. Yeah. You know what? That kind of looks realish. Click on it. That's where we're kind of like, you know what, there's some things that are totally obviously real, and then there's some other ones in these images that are like, yeah, maybe not.
Well, and I'm looking at this sucker right here. Sorry, I'm right on top of my mouth, getting close to my screen. That I look at all of the rest of these crazy crescent moon things in the image, and this crazy crescent moon has a growth attached to it. And I'm going to click on the growth because it's different.
Exactly.
And so this is 4 potential discoveries made during the hangout.
Yay!
So I'm going to stop clicking so that I can actually pay attention to my guests. But this is my encouragement, and I'm going to click done working so that I don't lose that. this is your ability to be part of a NASA mission. And what's kind of awesome about this is there's a whole team of researchers that are working on this, and they're working to submit all of these things to the Minor Planet Center, which is, there's rules. So when the paper goes in, it has the observers' names on it, and it has the names of the people who've spent all the time on the computers doing this, that, and the other thing. But then we also list within the paper the names of every single person on the project who's contributed to a discovery. And so I've had my name on this, and I'm a stellar person. I do variable stars, very different from studying the icy Kuiper belt. And so this is just a great way to actually be part of science. And it's not an instant process. It's actually a whole bunch of different objects got submitted last March, and only 2 of them have made it through to publication so far. So if you could talk about all the different steps that go into going from the one set of clicks I just made on one image to taking it from that one image to everything you need from all the different images to get it published.
So I would actually take it a step further back, because there's all the strategy that goes into getting the photons, which we then feed to the hungry, eager minds of the ice investigators. And so it starts with, as JJ described earlier, we have to strategize and work out where on the sky we want to target our imagers. And that was in the works for quite a while before we actually started the current effort. And so we prioritized an area of sky which contained a large fraction of all the objects, which, given the orbital distribution of the Kuiper belt that we think we believe, and how these things should propagate forward in time, we thought that this would be the best place to look. Then we applied for time on a number of facilities, including Subaru on Mauna Kea, CFHT on Mauna Kea, and the Magellan telescopes in Chile. And we're awarded some amount of time on all 3 of those. And then we travel to these places, except in the case of CFHT, which has the marvelous queue system. So they have professional observers there at all times who just magically take data for you, and it shows up in a directory, and it's wonderful. But otherwise, I have to put myself in an airplane and fly to Chile, and then you go into the dome and spend a few nights. Hopefully it's not windy and you don't have to keep the dome closed, or it's not cloudy or raining. And you can collect photons on your imager, and then you load all of that onto a portable hard drive, because you collect far more data than is feasible to really kind of pipe through the internets back home. Yeah. So you carry it back on a portable hard drive, and then we do our image processing magic on it, in which we try to remove as many of the stationary sources as possible. Feed the result of that out to the waiting ice investigators, and when they click on a source, they've now given us a single point and said there is something here that is either changed in position, in time, because it wasn't there in the stationary catalog, or it's changed in brightness with time. So a variable star could also show up. Yeah. So once we have that single point, and we say there's something of interest here, and so we can then take the metadata of all of this, all of the locations that people have clicked and the times that they clicked, and you can look for detections that fall along a line. Essentially, with time, they travel along essentially a straight line over short periods of time. And once you have that, you have a pretty good piece of evidence that this is something that's moving and not something that's just varying in brightness. So that gives you the initial estimate of an orbit. And so once you just have that sort of single night detection of something moving along, like that video we showed earlier, that was just over a few hours. And that's the sort of data that we first make a detection of a moving object in. Once you have that, that doesn't really give you the orbit around the sun. It gives you an estimate of how far away from the sun it is and the tilt of the thing's orbit with respect to the Earth's orbit. But you don't get a whole bunch more information than that out of that first night. But what you can do with that is predict where it will fall for the next few weeks, maybe a month, with relative okay accuracy, where it will be on the sky. And so then we have to come back with our telescopes again and image the area of sky where the thing should be, and hope that we find it again. And so once you then have sort of a few weeks to a few months, you can really start to hone in on the actual orbit around the sun of the object. And that's what you need in order to determine if the object is going to be encounterable by horizons. Because we have to be able to predict not a few weeks ahead, we have to be able to predict years ahead. So the the first TNO that will fly by at any sort of reasonable range from the New Horizons spacecraft that we found will fly by at the end of next year. It'll fly about 1.2 AU away, so not very close on the scale of things. It may be detectable at the extreme limit of some of the instruments on board the spacecraft, and we're looking into that now. But that's the first. And then after that, there's one more that we found that will fly by the spacecraft before it gets to Pluto. And then after that, the next one isn't until 2016 and 2017. So it's years. We have to predict these orbits for years. And there are some that won't encounter until sort of 2020 timeframe.
Wow.
And so none of these yet are objects that I shouldn't call them encounter targets, because they're still too far from the spacecraft, even at their closest approach, for the spacecraft to reach them and fly as close as it wants. But they will come pretty close. And so by pretty close, some of them come down to 0.1 AU. And that's close enough that these objects, if they're large enough, we could detect them with the cameras on board New Horizons. It wouldn't be like a nice resolved map of the thing, which is what we'd like, right? But they would be something that we could detect with the instruments, and we could look, say, for small moons, or we could learn more about it than we might be able to learn from our limited vantage point here on Earth. And so that's where we are now. Once the reason that there were only 2 of those objects that were submitted earlier this year ended up in the Minor Planet Center, sort of the official database, they were classified, is because the Minor Planet Center has rules about the quality of an orbit that it will accept and give a name for. Because essentially, if everyone who ever detected a TNO or an asteroid and had detected it on a single night with a few hours of arc, submitted that to the MPC and they accepted that and gave it a name and everything, there would be many, many of these things in there. And the unfortunate thing is, like I said, you can't predict where these things will be with any accuracy after, say, a few weeks. So essentially, these things would get names, they'd build up in the database, but then we wouldn't know where they are. We would lose track of them. And so they're not actually very well classified at that point. And so the MPC only accepts things that are reasonably well classified. And so they have some length of time, which they consider the minimum length of time. They call things that have been observed on a single night a one-night stand. And you can't, they don't accept those because there's just too many of them. And so those 2 that were accepted were ones that had reasonably good orbits. We had a pretty good idea of what kind of orbit it's on around the sun, not just where it's going to be in a few weeks. And so those were the really well-characterized ones. The other ones that were submitted only had much shorter arcs. They had been observed for a much shorter period of time, and so we didn't have as good a measure of its orbit around the sun.
So hopefully over time we'll be able to build up a larger set of things that have high-quality orbits.
Yes.
Now, I see that Aaron Haviland is asking if Ice Investigators is an evolution of Ice Hunters. I think the answer is sort of. What happened is the Ice Hunters project had a set of data in it that was from the 2004 observing season. We completed all of that data and submitted everything for publication. And then CosmoQuest started to come into existence. And CosmoQuest is a new type of community that does things like this hangout, the virtual star parties that were highlighted by Google earlier today. We have news roundups. And so we're a place to not just do science, but also to learn science. And this is something that's completely new. And the New Horizons team jumped on board, and so now we're working within this new environment. It's the exact same group of people, the exact same team of scientists, the exact same team of programmers. We're just doing something that allows us to not just ask you to click, but to say, hey, let's chat with the scientists on Google+. And so this is where the change originated, was we wanted to move within the CosmoQuest family and be in a position to help give you more information, updates, and up-close experiences with your team scientists. Now, as we move forward, one of the things that I know lots of people have in their head is, awesome telescope on its way to Pluto. We'll get Lunar Reconnaissance Orbiter style images and fly through Han Solo's asteroid belt. What are the realities of this mission? Why can't New Horizons just open up its shutter and observe ice in all directions and find its own targets for flyby?
The Kuiper belt's really far away. That's the fundamental point there. It's really far away. So it's billions of kilometers from the sun. And it's cold, and more to the point, there's not a lot of light out there. So
it's so cold.
Yeah, exactly. So the further you go from the sun, if you double your distance from the sun, the amount of light that is hitting you from the sun drops by a factor of 4. So, and it goes as the distance squared. But so what makes it challenging for us is that we're here on the Earth. So the light actually not only does it have to propagate out from the sun to the object, it has to propagate all the way back. And so it also dims as d squared all the way back. So overall, you get this distance to the 4th power drop in luminosity. This spacecraft, however, since it's already out there, only has to deal with the d squared. But that's enough. So the Kuiper belt, so the first Kuiper belt object that will fly by at that sort of 1.2 AU range, it's about 28 AU from the sun. So it's slightly closer to us than Neptune. So I guess I should call it a cis-Neptunian object because it's on this side of Neptune. But even so, that's roughly 30 times as far away from the sun as the Earth is. So that's 30 squared times less light that is hitting that object than the Earth receives. So per square meter, it receives 30 squared times less light. So these objects are not bright. They're very faint. And so if this telescope could open up its shutter and just stare, it would take a long time for it to just chance upon an object which happened to be close enough and happened to be bright enough for its detectors to pick something up.
And how big is the mirror on New Horizons?
It's of order 8 inches, I think.
Yeah, so this is your Meade 8-inch, your Celestron 8-inch. So think about the types of stuff you do with your backyard telescope. So even though you're not dealing with the atmosphere, so that makes things a little bit more crystal clear. You're not getting the atmosphere blocking out certain wavelengths of light. It's still an 8-inch telescope.
Yeah, I mean, that's the thing, is that when you get out there, you really are just looking at this thing with your backyard telescope. You might say, well, why are you spending all of this money to send a Meade, like an 8-inch telescope, to Pluto? But when you get out to Pluto, right, when you get really close to the object, that's really all you need once you're up really close. And so you know, yeah, you can't look at Pluto right now because it's too darn faint. But
Yeah.
you know that we're going to get a heck of a lot closer, and that's going to be a sufficiently good telescope to do that work. And the bigger you make the mirror, the more it's going to weigh, and the more it's going to weigh, the slower the spacecraft's going to go, or the more fuel you have to put on board, and the more expensive the whole operation becomes. And so there's a trade-off that we do to say, what is the heaviest thing that we're willing to, put out there to make this kind of observation? And when you realize that you're going to get this close to the surface of the object, well, you don't need a giant telescope anymore. You just need to get close.
Yeah. Think of the fabulous views that 8-inch gets you of the moon.
Exactly.
And that's what we're looking at. Now, I have Nathan Broussard asking, space is so empty. I really hope they find a candidate too. Are there any estimates of the chances of finding targets? So what's the probability that you're going to find these 1 or 2 critters that passes right through your cone using our modern understanding of the densities within the Kuiper belt?
So there's a 100% probability that there is one object, there is at least an object in there at some size, because the smaller you go, the more objects there are. But the question is not so much what's the probability of there being an object in there, it's the probability of us having sufficient resources on telescopes on the telescopes that exist on the planet in order to find that object or an object.
Yeah.
And I've done some estimates based on what we've found so far, and so you can estimate how the number of objects should scale as a function of how close to the spacecraft it will get.
Yeah.
And based on the objects that we found and how close those will get, we need to find roughly twice as many objects as we found so far. And I don't mean overall, I mean in the last observing season we found roughly 20 objects. We need to find roughly that many again, and there will be that should be sufficient to find one that we can encounter. And out of that 20 so far, or roughly 20, there are a few possible, we have short arcs on some of them, and we can't tell if they're asteroids much closer to us or if they're TNOs further away. So those are sort of fuzzy cases, but most of them are definitely TNOs. Many of those come, like I mentioned, within sufficient range to be observable by the spacecraft. They're just not our juicy, we're going to fly by and get maps and images of the surface kind of thing. And so at this point, we already have a sample that we will do science on, we hope. So they're bright enough to be observed from the spacecraft. We can look for moons, which is a very valuable science case. We know that the larger objects in the Kuiper belt frequently have large moons, sometimes as large as their primary object, so they're binary objects. And as we go down to smaller and smaller sized objects, we don't know what happens to those moons. Do small objects also have moons? And that would tell us a lot about the history of the Kuiper belt and whether or not there was ever an epoch of strong collisional evolution where objects were slamming into each other. And if that happened, you wouldn't expect small moons. But if the Kuiper belt was never subjected to a period of intense collisional bombardment, then maybe those small objects will have moons. And so maybe these small objects that we fly by will see little satellites going around them. And that's really what we'd like to check.
Now, one of the things that really works in your favor is Kuiper belt objects are largely ice. Ice is one of the most reflective things that we have. And so unless we end up with any that are covered in really dark organics, which we've seen in some examples of various moons, they're at least shiny and they're going to reflect more light than an asteroid.
Yeah, they're not as shiny as you think they are.
Really?
Yeah, like the typical Kuiper belt object is quite a bit darker than the surface of the moon in terms of its reflectivity.
Oh, no.
Sort of somewhere between charcoal and asphalt.
Yeah.
So it's not getting resurfaced nearly enough.
No.
We don't totally know what's going on with these surfaces, and this is one of the reasons we want to fly by. So
this is one of those things I learned wrong in grad school, so this has changed in 10 years.
There are objects out there. I mean, we assumed that they were made out of ice and that they would be pristine and that they would not have a coating of charcoal on them or whatever.
Yeah.
But as we've had better and better estimates of the actual reflectivity of these surfaces, our understanding of the distribution of reflectivity has shifted, and we think they're for the most part quite dim. There are some, most of the bright ones. There are a few which are very, very reflective, and most of those are part of what we think is a collisional family of objects. So there's one large object in the Kuiper belt called Haumea. It is shaped roughly like a football. It's quite sizable. It's longer on one axis than Pluto is wide, but it's quite narrow on the other axis. It spins very quickly. It has two small moons, which are also very bright. The surface of this object looks like it's made out of absolutely pure water ice, just this shiny, super bright. And there's other objects which seem to share its orbit, or similar orbits to it, that also have shiny water ice-rich surfaces. So we think what happened was that this object got smacked. Its mantle of ice was stripped off, and it formed this cloud of other objects. The impact spun it up, which stretched it out into this sort of elongated football shape. So those objects will have albedos that are quite high, and some of the other very large objects. So Pluto has quite a high albedo, and
albedo is a fancy word for how shiny it is.
Yes, it's
So there's a weird thing. So Eris, the biggest object in the Kuiper belt, Eris has a reflectivity which is basically more light shines off of it than actually impacts its surface if you do this math slightly incorrectly. I mean, it's just perfectly, it reflects everything. It's like the perfect mirror. I sometimes look at the people's calculations and I think, if we could build telescope mirrors from the same stuff that the surface of Eris is made from, we'd be in business now. But so it's very, very reflective. I think Eris probably wins the competition for the shininess surface. So,
yeah. So it's like Enceladus for its. We think it's just fresh frost on the surface essentially. So it's reflective like freshly fallen snow, and that's again it's one of the biggest objects. So it can have an atmosphere which is frosted out, and it'll hold on to this volatile material which otherwise would boil off into space. These smaller objects don't have that luxury, so they're just coated in whatever the non-volatile materials that can stick around for the age of the solar system. And there's other sort of mysterious components of these surfaces. So some of them are they have quite a red color. So they reflect more red light than blue light. And whatever material is reddening them, you go to meetings about this, and people will talk about what they think is the reddening material and the justification for that. And it could be irradiated organic materials. It could be some mix of hydrocarbon gunk on the surface. But we don't know. There's no easy way to tell. There doesn't seem to be any nice indicative sort of spectral features that you can hone in on and say, this must be this particular hydrocarbon goo or something. So what we really need is some handy little spacecraft to fly by one of these things. And that'd be
know where to find one of those.
Yeah, I know. It'd be great if we just had them laying around somewhere.
I think someone should write a proposal to do this.
Yeah.
So I have to admit, one of my very first observing runs when I was a baby grad student at the McDonald Observatory was with Anita Cochran, and we were doing a Kuiper belt object search, and she was training me on how to use the 107-inch. It has an imaging GRISM camera that I used for a ton of my research, and I needed to use it the next night to look at galaxies. My heart belongs to variable stars. My dissertation belongs to the extragalactic part of the universe, and so when we were out there, I learned there's two strategies, and I'm actually seeing this in the differences in the observations we're getting from JJ and that we're getting from Mark Bowie, who unfortunately isn't in this hangout tonight. There's two strategies for looking for these suckers. One is you move your telescope at the rate that you expect the Kuiper belt objects to be moving, and the other is you move your telescope at the rate the stars are moving. Can you give some explanations of why the two differences?
Sure. So if you have a small telescope, you're going to have to take a lot of exposures to see faint objects.
And you're using CFHT, which is how large?
It's a 3.6 meter, so it's really quite small compared to things like the 8-meter telescopes that we're using on the other sites. And remember that the collecting area is what matters, so it goes as the square, basically, the size. So with the 8-meter telescope, you can take a short exposure, and you can kind of get the depth that you want. If you take a longer exposure, it won't actually make you see smaller objects in the Kuiper belt because they're going to start moving. And as they trail across the image, they'll be against more sky background, they'll enter more pixels, there'll be more noise, and so you won't get any deeper. So with the CFHT telescope, once we've taken an exposure that's more than about 200 seconds, we're really kind of starting to get to the limit of how long an exposure you can take and see an object moving. But it gets worse because the galactic center is in the way, and so when you take an exposure with CFHT of the galactic center, all these stars are so bright that what you just end up with is white. There's nothing there. If the stars all saturate, yes, Olber's paradox. It just completely fills the camera. There's nothing left, and so you have to take short exposures so that there's at least some space that's dark. And the reason it's dark is because, well, you didn't get as deep in those locations. You didn't see the fainter things. Then what we do is we work really hard with those short exposures to take out the stars. We've developed some algorithms that basically try to match the shapes of stars from one image to the next and subtract away the stars that stay in the same place over the course of a long period of time. And in fact, we use exposures taken a year before our science exposures. We take these kind of calibration exposures that tell us where the stars are. And we use those to then subtract away. So we know none of our Kuiper belt objects are being subtracted away. Only the stars are being subtracted away. And we do that, and then we're left with these images which are just kind of basically blank and noisy. And we say, okay, if there was a Kuiper belt object in there, where would it have gone from one exposure to the next? Because these exposures are only 90 seconds long. Let's take the digital image, let's put it into software, and let's shift it along to compensate for the object's motion so that the object in the Kuiper belt would look like it's standing still. But there's still some stars left in these images. Some of the really bright stars are hard to subtract away. And so what we end up doing is saying, okay, let's do those trails, and you start to see the trails of stars showing up. These bright stars look like these streaks across the image, and then every now and then there's a little point where you say, aha, that's my Kuiper belt object. That's what I was looking for. Now they move based on the Earth's motion. Basically what you're seeing is reflex motion. The Earth's hurtling along through its orbit. Those Kuiper belt objects aren't really orbiting very much in that period of time. They are moving, but not quite as quickly. And so we see them shift in their position. And the amount of shift that they have, their rate of motion, is dependent on how far away they are. So each rate of motion that you would expect, you have to kind of make a stack for objects. We're making stacks for objects that we think are at 40 AU. We're making stacks for objects we think are at 42 AU. Another one for 44, another one for 48. And that's why there's lots and lots of stacks to look at.
And the way to think of this is if you hold up your finger and move your head, your finger will appear to move relative to the background. And as you move your finger further and back, keeping it in place and only moving your head, the amount that your finger appears to move relative to the background increases as your finger gets closer to your head and decreases as your finger gets further from your head. So it's just Earth moving and Kuiper belt objects sort of kind of moving, just very, very slowly.
Yeah, exactly.
So we're coming up on the end of the hour. I see one more question that we haven't answered so far in the comments, and this is coming from Tim Hem. And after I ask this and get an answer, I'm going to ask you for some closing thoughts, so if you want to start thinking about your closing thoughts. Tim Hem mentions that he'd heard that Pluto might have some sort of a ring around it, and I was wondering what's the science in that? What are some of the concerns that you have to worry about in terms of objects you aren't anticipating as you fly a little too close to the system?
So there is some concern in that. So since launch, they found first Nixon Hydra with the Hubble Space Telescope, and then later they found another moon, which is much smaller and which is much more difficult to detect, and that one doesn't have a catchy name yet. But the presence of this, even this extra moon, which was in between the orbit of two of the other moons, it's sort of like this system is really full of stuff, of little objects packed into very tight configuration, and so something had to put it all there. Either likely what happened, there's a variety of models for where the Pluto system came from. So it could have formed in a large collision, and the motion of Charon outward with time could have caught the smaller moons in their current orbits. But the thing is all those sorts of scenarios all say, well, there should have been a lot of junk in the Pluto system at one point or another, and maybe there's more of it there that we haven't seen yet. So there's two kinds of junk that they worry about, and they're related. One of them is other satellites. So on one hand, that's great, because it just gives us more objects.
And this is natural satellites, not other versions of New Horizons.
Yeah, not other robots out there already. No, other small moons orbiting around the Pluto-Charon system. And those would be great to find, because they just give us more targets to image as we fly by. But at the same time, more small satellites just mean more surface area for little, essentially micrometeoroids to impact and blow off small amounts of dust. And every time that dust goes out, some of it hangs around in the system for some time. It gets stuck in temporary orbits. Yeah. And so you could conceivably put satellites in certain places where these ongoing little impacts could produce a semi-stable sort of donut of material, of dust. And it wouldn't take a very large piece of dust hitting the Whipple shields on the front of New Horizons to completely wipe out the spacecraft. And we're talking, by pretty small, I mean something of order the size of a grain of sand. If that nailed the spacecraft at 13 kilometers per second, which is how fast the spacecraft is going to be zipping through the Pluto system, it would be a tragedy. And so what they're working on right now, there's two sorts of fronts. And one of them is we're taking the Hubble Space Telescope and we're pointing it at the system and going as deep as we possibly can. And the thing is, not only do you have to look at it for a long time, but you also have to do it very carefully so that you can remove Pluto and Charon, all the bright stuff, and just leave behind a ring or another satellite. So that observational effort is going on. Additionally, when the spacecraft, a few weeks out, the spacecraft will actually have a better vantage of the system than the Hubble will. So it'll be able to evaluate whether or not there's any dangers. And they're working on what they call a safe haven bailout trajectory, or Shabbat. And the idea is that at that point, it will say, look, there's this ring there. We're going to go to our safe haven bailout, where we've already worked out that that area is unstable. There can be no dust there. So we'll fly through that region, and it should be safe. And that's the other work that's being done, is sort of is theoretical, where you're taking these systems and saying, where can we put a moon? And it will stay there for the age of the solar system. And this moon could be hammered by micrometeoroids and produce dust. So can we actually even conceivably stick a moon in that could be producing dust? And there are some reasons that you could argue either way, that maybe a moon could exist here or not. There's an interesting upper limit you can put on the number of other moons you can put in the system, because the current moon that we know of, the current smallest one, which is P4, this little guy, it resides in this tiny little bubble of stable space, of stable orbital space. And if you just nudge it a little bit out, it would become unstable and it wouldn't exist anymore. And so all it takes is a tiny collision with a tiny impactor in order to do that kind of, by tiny I mean sort of 1 kilometer across, which is tiny on the scale of Kuiper belt objects, might be sufficient to bump it out of that stable region. So we can limit the total number of impacts that can have happened over the age of the solar system in the Pluto system, which might generate a lot of dust. So those are sort of the two fronts that people are taking to look for additional satellites and rings, and the dangers inherent in that, and how we're hoping to mitigate them.
And you also get a certain amount of ability to limit moons just by what orbits you're able to see. If there were any more large moons, there'd be deformation of the existing orbits. You might have to worry about resonances in certain places. So you can, mathematically, thanks to orbital dynamics, do a fair amount of ruling out of invisible, deadly, large things. It's, as you said, the tiny things that are the death knell. Now, I'd like to end on a more positive note than things that could destroy the spacecraft. We're looking forward to the post-2015 encounter. We're looking forward to going out, sending the spacecraft to a target that was viewed in ice investigators by some of the people who may be watching this YouTube video right now. What do you have to say about the things you are most excited with as this mission moves forward? What parting words do you have for our audience?
Well, I'm excited because of well, a few things, but first and foremost is the sudden appearance of that we're upon the Kuiper belt now. So we have some targets that will be flying by, like I said, the end of next year, and these ones are, you know, they're not choice targets because they're pretty far away on the scale of things, but we're there. We're passing the first Kuiper belt objects next year, and this is something that's been, you know, I got this current position last year, but I've been thinking about it since I was sort of in grad school, and it's all been, you know, I'll work on that down the line, and we'll get to the Kuiper belt. It's years from now. Okay, but now it's next year, and then after that, there's another close flyby that'll occur just before the Pluto encounter, and so we're entering the Kuiper belt. We're in that space now, and no one has ever sent a spacecraft. I mean, we've flown Voyager through there, and some of the other spacecrafts have flown through, but we've never entered the Kuiper belt and known that we were going to fly by objects at a range that is sort of conceivable that we might be able to see them from a spacecraft. So it's really quite an exciting time, and the next few years will be pretty remarkable, I think, because it will be within the next few years that we know where our candidates are and how close we will be able to get to them, and not only the ones that we'll fly really close to, but other ones that we'll fly at large distance from. There will be a much larger sample of ones that we can see at reasonable distances than the few that we can fly by at short range.
So JJ, what parting words do you have for our audience?
You know, every time we think we understand something in science, very often what happens is that you have a kind of a model that builds up in the scientific community, and it turns out that there's some piece of evidence that comes out that shows how totally wrong you were with your model. Because your model was based on a lot of conjecture and a lot of ratty data. And what really helps is when you can have some real truths in science that will really lay down, this is how things really must be happening. And when New Horizons starts getting to objects like it starts getting to Pluto, and when it starts getting close-ups of Kuiper belt objects, we're going to have a whole mess of new information, of new truths in what's going on in the Kuiper belt, where a lot of the arguments, a lot of the paradigms are going to slide away because we're now going to understand something that we currently don't.
Now, one thing I'd like to share with you just for the humor of it is we're working on a staff t-shirt for CosmoQuest, and this is something that you guys will be eventually getting for the work that you've been doing with the ICE Investigators team. And the origins of this shirt are, I went to an artist we've worked with in the past, Chris Spangler, and I said, okay, take the best images we have of our solar system, think Andy Warhol, come up with something bright and beautiful and inspiring about our solar system because, well, CosmoQuest is right now focused on the solar system. When we first saw this, my other staff scientist, Nicole Gallucci, and I, we died laughing because of poor Pluto. Because there are no good images of poor Pluto. So our beautiful, artistic, modern art version of the solar system has the overly pixelated Pluto that the New Horizons team is going to be able to replace with an understanding of just what that surface is going to look like. So I thank both of you for being here. I thank the audience for being out there. This has been the CosmoQuest Weekly Science Hour. Next week it will be hosted by Emily Lakdawala. If you want to keep track of this and all the other CosmoQuest events, you can either follow our calendar at cosmoquest.org/blog/calendar, or even better, sign up for an account at CosmoQuest. There is a checkbox in your user profile to get a weekly newsletter. It's the only email you'll get from us each week. And we include information on this Hangout and all the others that we do within that newsletter. The next Hangout will be tomorrow morning at 10 a.m. Pacific, 1 p.m. Eastern, and that will be hosted by Fraser Kane. It's our weekly Space Hangout, which is a roundup of all this week's news coming to you from the journalists such as Alan Boyle from MSNBC, Ian O'Neill from Discovery News, Nicole Gallucci, Discovery News and CosmoQuest, and a whole team of others, Universe Today. It's a great group of people. Go find out what's new in our solar system, and we may be sneaking in a recording of Astronomy Cast either tomorrow or Friday. And then, of course, there's going to be our weekly Star Party Sunday night. Due to the summer months here in the Northern Hemisphere, I'm afraid to say that that won't start until 9 p.m. Pacific, midnight Eastern. We desperately need some Southern Hemisphere observers. If you're a Southern Hemisphere amateur astronomer, please get in contact. We'd love to work with you. So this has been the Weekly Science Hangout. I can't thank you enough. I've had with me tonight Alex Parker and JJ Kavelars, and go out, help us discover the universe, do ice investigators at cosmoquest.org. Thank you all so much.
Thanks very much, Pamela.
Thanks.